So 70,000 times, we had a 70,000 times advantage. That's all got washed out. Uranium, much more expensive to dig. It's not like natural gas. You go Texas, look at the site really hard, and suddenly gas comes up. You got to dig it out. You got to purify. You got to convert it. You got to enrich it. That completely washed out. Now we're talking about a factor 2.
A warm welcome back to Decouple. And welcome back, Koroush Shirvan, for your second episode. For those who do not know Koroush, he is a professor of nuclear engineering at MIT, specializing in development and assessment of advanced nuclear reactor technology, currently focused on everything, it sounds like, but in particular, accelerating innovations in nuclear fuels. And that is what we are having Professor Shirvan back to talk about today. So welcome back.
Yeah, thanks for having me back, Chris.
Awesome. So I figured for today's discussion, we're going to stick away from uranium mining, milling, conversion, et cetera, and really focus in on those beautiful, fuel bundles. What's inside them, claddings, new fuel types, some of the economics of all of that. I always love getting a historical perspective, so I'm interested in what the hell was inside of, Fermi 1 and 2, if we can go back that far. I'm not dwelling on that too much. But yeah, just get a sense of what's happening, what's developing. So that's my agenda. Why don't you take it away?
Yeah, thanks. This is an opportune time to talk about nuclear fuels because both the uranium markets and enrichment markets in terms of cost has gone up quite a bit. And so it's important to put these things in context. And I'd like to start by, taking us back of why we have such a great support for nuclear fission since the beginning. And that support always comes down to the energy density of the fission reaction. So when fission was discovered and people start thinking about using that energy for power production, the main incentive that drew people to it was that a split of the uranium-235, which is the fissionable isotope of uranium, generates 70,000 times more energy per unit mass as methane combustion. Methane is commonly known as natural gas. And so you would need by mass 70,000 times less fuel to generate the same energy. Now, natural gas plants do convert heat energy to electricity at roughly twice as efficient as conventional water-cooled reactors. So then it becomes to 35,000 times, which is still quite impressive.
And part of that is, thinking about how the fuel gets to the plant. And I understand that was something that was attractive early on to people looking at nuclear for electricity. You got to build, big railroad track, transport lots of coal to the plant or natural gas pipeline. And so nuclear was attractive because you could deploy it to areas that did not necessarily, say, have coal, like my home province of Ontario.
Yeah, exactly. And the other side of it is, then on site, you can just, store very little amount of volume of fuel and be set for years versus, fossil fuels where you have to pile up a lot of coal if you want to have that energy security for years.
So let's go back in deep time to, I guess, Manhattan Project and talk about what the earliest fuels were.
Yeah, so, because uranium is mined, more or less, uranium is a metal in nature. So early on, of course, the attraction was, why don't we just use uranium in its metallic form? Very quickly, it was found that pure uranium itself is not really stable under radiation. I always show this plot to my class that after about almost a few days of radiation, the uranium slug grew in like 3 times in length, became basically spaghetti. And so you of course don't want that in your system. So then the work became, okay, how can we stabilize this uranium? And people went different directions. different. They added different metallic alloys, aluminum, zirconium, iron, different things. And they found that indeed you can, stabilize this. And then they explored ceramics, from oxides to carbides, later on silicides and nitrides. And then, there were also a group of people where, some of the ceramics, like the oxides, they tend to be not very good at transferring heat. So that ends up, realizing very high fuel temperatures. So then they explored what's called class of system called the cermets. So this is a ceramic metallic. So you have the uranium oxide, which is very stable under radiation and can fission and not, go through a lot of dimensional changes. At the same time, you can put it in a metallic matrix, and that metal can conduct heat out more efficiently, as well as it's relatively ductile. And allegedly, there are some thesis from MIT actually that mentioned that, the naval reactors have been interested in this CERMET type fuel. And then when you look at also other applications, space reactors have also been interested in CERMET type fuel. So you really have, three classes: oxide, ceramics, metals, and CERMETs that kind of in parallel developed for a variety of different applications.
Suffice it to say, it sounds like most fuel that's used commercially nowadays is some form of a uranium oxide. Is that correct?
Yeah, and people actually don't realize how extended its use is. So, from water-cooled reactor that make up over 90% of the nuclear reactors around the world, whether it's a pressurized water reactor, boiling water reactor, pressurized heavy water reactor, graphite moderated water-cooled reactor, they all use oxide fuel. The gas-cooled reactor fleet in UK also uses uranium oxide fuel. A lot of the past fast reactors, these are typically sodium-cooled reactor. Overseas, majority by all use oxide fuel with different uranium and plutonium. In the US, currently we don't have any fast reactors. That was one difference, that in the US we did utilize metal fuel for our fast reactors, as well as Russians for some icebreakers and some, unique technologies. They use metal fuel, but by and large, oxide fuel is the dominant fuel because, very stable under the harsh conditions of radiation and fissioning, tends to actually keep over 95% of the fission products to itself at, temperatures that we operate at. And it's already an oxide. So when you expose it to air or water during normal or accident conditions, the fuel form's not going to change chemically to a different form.
So you were explaining before that the uranium oxide, it's a ceramic, it doesn't transfer heat quite as well. There's theoretical benefits in a metallic fuel. That being said, I've heard it described before that, the nuclear reaction actually made that promise of alchemy, of converting one element into another, made that available to humanity. And, what's going on is very complex chemistry inside of that cladding. And so, as you mentioned, the original uranium metal fuels growing so much under bombardment. I'm wondering if we can nerd out just a little bit more on what the hell is happening, because I think that's underappreciated in terms of the complexity, again, of nuclear fuel, that neutron bombardment, fissioning, creating new elements. Walk us through a little bit more of that, if you don't mind.
Yeah. And I usually say with a nuclear fission reactor, you basically have all the elements in the universe inside your little fuel pin, because you're literally creating and what we call, transmutation, taking, one element to become another element. And the whole fission process where it splits the uranium nucleus, it doesn't always create the exact two elements. It's actually a distribution of those. So you got the whole things happening. And part of this is some of these elements that are created, certain isotopes. So we have elements in the periodic table, and then we have isotopes that have different number of neutrons of the same elements. So they have same chemical affinity, but in terms of radioactivity, giving off radiation in different forms, they're very different. And those isotopes of these elements can be very radioactive. And this is where the whole point of why nuclear has its own regulator versus, a normal thermal power plant where your hazards are, mainly chemical in nature and energetics in nature. Here we also have the radiation component. Some of these isotopes, cesium and iodine, which is being by far the top ones, we want to make sure that they stay in the fuel. One of the reasons why you see from outside, okay, I got, that 70,000 times energy density, but my plant footprint is not really that much smaller than the natural gas footprint, is that all those systems, all those structures, and all those containment, all those auxiliaries are there to keep that radioactivity within the fuel. So inherently, if you can do something to the fuel, that it can actually keep most of it inside and not easily chemically react with the coolants and the environment around it such that it gives it off, that becomes a very important design goal. And then, to help keeping all that in, because not all these fission products remain solid at the operating temperatures of the reactors around the world. Some of them are gases like xenon and krypton. And in that case, I also have to have some kind of a casing that cases all this radioactivity inside. And again, designing that casing such that it's durable, it works when you need it. It works when you're storing it for years for the reactor for the nuclear fuel to cool off and potentially eventually dispose of it. Becomes critical part of the nuclear design and how that cladding also works with all these safety systems and the overall nuclear structure. It's all very integral and heart of what nuclear engineering is.
Thematically, I'm sort of sensing a commonality here whereby, when we look at the global nuclear fleet, it's almost exclusively water-cooled, water-moderated fleet. Despite compelling narratives that, we could have higher thermal efficiencies with gas reactors, for instance. Similarly, the dominant fuel type you're mentioning in reactors around the world is uranium oxides. Despite, again, there being, nice narratives about, potential advantages of more exotic fuels. Maybe just a kind of closing statement on why that is. We're going to get into talking about cladding and then I think accident-tolerant fuels, where we're going to talk a little bit more about, what some of the potentials are in terms of modifying the actual fuel type. But I guess just one more, thematic statement on why, again, there's this supremacy of uranium dioxide in the reactors around the world.
Yeah, so when you look at reactors around the world, which are, again, as you mentioned, water-cooled reactors, the hydrogen in water makes all these reactor what we call very unfortunate name of thermal reactor, which has nothing to do with the thermal power, that the heat that they generate. So then you transfer to electricity. It has to do with thermal, is just another way of saying slow. The hydrogen slows down the neutrons that are produced as part of the fission process. Those neutrons scatter off these hydrogen, they slow down, and now you have much greater probability of fission. Everyone, I think, that probably hears your broadcast knows something about enrichment. Enrichment is about putting more and more the uranium-235 isotope into that oxide fuel. Because the more U-235 isotope I have, the more chance of fission I have. So water already increases that. And as such, all these reactors that we're running around the world that are thermal reactors use less than 5% enrichment. And uranium has a decent packing of uranium oxide has a decent packing of uranium inside of it. And so when you're looking at, going to a different fuel form, let's say you go to a metallic fuel form, in order to stabilize it, you need some zirconium inside that fuel form. And that zirconium requires some neutrons. So now you've displaced some of the volume of uranium with zirconium, and that zirconium interacts with neutrons. So it's not as transparent to neutrons as oxide fuel. So from a reactor physics point of view, there's also certain advantages behind UO2. But mainly, the other aspect that's very important is this enrichment level. And just having water, whether it's the light water or you guys in Canada, the heavy water, that's what really keeps the enrichment that goes into this fuel, which is one of the main drivers of the cost of the fuel for the oxide fuel.
So hence why a lot of the so-called Generation 4 designs, high-temperature gas reactors and others, are requiring higher enrichment levels.
Yeah, so that's part of it. So as I mentioned, the UK reactors use uranium oxide at less than 5% enrichment. So why would Generation 4 gas reactor use high enrichment? In fact, they could utilize low enrichment. The key part is that they've moved away from the oxide form, which is you have a pellet, which is centimeters roughly in diameter on that order, and then you encase it in a cladding. In case of the UK gas reactors, a non-zirconium-based cladding, and in case of other water reactors, the zirconium-based cladding. What they do in the Generation 4 gas reactor, they actually reduce the total available volume of fuel into a little bit of TRISO particle, little small spherical pencil tip size particles, which in China, it's made out of actually uranium dioxide. In the US, a lot of the program, it's focused on uranium moxicarbide. It's basically uranium, carbon, and oxygen. And then they encapsulate this in different layers. And because now you have much bigger volume invested in capsulating little fuel particles, you've reduced the amount of fuel volume you have. And so you have to enrich it more in the uranium-235 in order to have the same fission probability as you would have with a classical large uranium dioxide. So it's not that they're using a different, let's say, fundamentally a different form. It's just that they've reduced the volume at hand, and that's why they have to do this. Now, different reactors do different things. So I'm sure you've heard of like the microreactors. In their case, they want to go for longer cycles, meaning that they want the fuel to operate more than just 4 years. They want it to 10 years. So that means that you need to put in more uranium-235. And then if you're reducing the volume by using TRISO fuel, that again pushes your enrichment up. And then I'll end with the last class, which is the fast reactors. So the reactors that do not have hydrogen or carbon to slow down the neutron, to increase the probability of fission, to reduce your enrichment levels. For the fast reactors, there you have to actually increase the amount of uranium-235 in your system, because now neutrons are going faster. There's less probability of them fissioning. So you have to actually inherently increase the enrichment, whether you're using UO2 pellets or uranium in metal form or whatever form you use. You have to always go above 10% in order to have a sustained fission reaction. So it rather the decisions behind what is the fuel geometry you use, and whether you're having a fast or a slow or thermal reactor, those kind of determine your enrichment needs.
Let's kind of shift gears a little bit to talking about claddings. You mentioned certain reactors can get by with steel. I think some use aluminum. Zirconium seems to be dominant. Fuel failures. There was a issue in Taishan, China, with some of the EPR fuel. I understand that was maybe a cladding issue. Those sorts of things, I think, have radically decreased as quality improvement has gone up. But let's talk all things cladding, if you don't mind.
So we have our uranium dioxide ceramic fuel that, pretty much all reactors use. And then because those gases, those fission products that are gaseous, particularly xenon and krypton, they get released from this oxide matrix. Not all of it, but some of it, small percentage of it, gets released. We have to have a way to seal this whole thing. It's convenient. It keeps these pellets that are centimeter sized, intact. And so we want to capsulate it with something. And that something has to have certain requirements because, again, we get our energy from fission. Fission happens because a neutron hits a uranium nucleus. And so that neutron needs to get to the fuel. So if I put an isotope of an element that sucks all the neutrons, that neutron will never get to the fuel. I don't have a fission reaction, so I'll not be able to generate power. So early on, they looked at different material. Of course, everything is very convenient to just use stainless steel for everything. And early on, one of the things that was, given to the nuclear industry by the government was fuel of your enrichment of choice. So you want 90% enrichment? Sure, sign up for it. Today, unfortunately, and I say unfortunately for good reasons. I'll give you a short example without taking too much time. On campus at MIT, we have a research reactor. That research reactor uses 90% enriched uranium. And the government has been trying to, for the last 15 years, almost 20 years, trying to convert that to, less than 20% enriched because, the International Atomic Energy Agency considers fuels that greater than 20%. They can be used for weapons. True, but who's going to come invade our reactor and take that fuel away? Or back in the day, who would have come and attacked these power plants in the U.S. and take that reactor? I mean, our closest neighbor is you guys, and so far we've kept it civil.
I don't know, our relationship's getting a little testy recently.
We kept it civil so far. Maybe
we did burn down your White House in the War of 1812. But anyway, carry on.
Yeah. So that's why in the U.S. we don't have that capability. Russia, you bring up a new a space reactor, a little reactor, icebreaker, whatever. It makes sense. I need a higher enrichment without changing completely the design. I'll just put higher enrichment, higher than 20% or higher than 5%. It's not a problem. But in the U.S., we've moved away from that. So that really limits what we can do. And so because we have such a limitation on enrichment, we have to make sure that this cladding material does not absorb neutrons, does not suck away our neutrons and leave it for fission. And so zirconium became, the choice because zirconium is a metal that doesn't really suck away neutrons. So we use it in all reactors. The other material that is used for TRISO fuel and also used for gas reactors for moderation is graphite, which is basically carbon. Carbon also doesn't really absorb neutrons. So you have to really make sure that, the coolant that you have, in the case water, is compatible with that. So for zirconium, we add a lot of minor alloying elements, 1 or 2% alloying elements, to make it robust such that it doesn't corrode and it maintains its strength at the temperatures that we like.
Is zirconium like a rare earth element? Is it limited? Is that a concern with the so-called nuclear renaissance that's coming? Supposedly?
Yeah, no, it's supply. It's not a big concern. It is used, in different industries as well. Early on, nuclear industry was its main user. So, just like with anything, costs went down quite a bit once the use came up. But we're not really that limited. If you look at cost of the a fuel bundle for CANDU or other reactors, very, very minor cost of the overall system.
All right. So I'm not sure if it's worth spending any time on like geometries of different fuels. They don't seem terribly different other than sort of the difference between prismatic and like the gumball machine pebble beds. I mean, I'm saying that as a, neophyte uh, nuclear enthusiast, and I'm talking to an MIT professor, so maybe I should roll back that statement. But is it worth spending some time to talk about geometry of how we arrange those fuel bundles and pins?
Yeah, well, I think what's interesting is we are kind of using right now for all these reactors again, UK gas cooled reactors to your beloved CANDU reactors to our pressurized water reactor and boiling water reactor, just bare cylinders that are supported, by different things, so they don't, bend or touch each other. But in the old days, again, it was kind of like mechanical engineers doing nuclear engineering. It wasn't like a nuclear was brainwashed that, hey, keep it simple. I can only analyze a cylinder with my latest, greatest, computer codes. So what do they do? A lot of these fuels look like they had fins on them. One of my favorite fuel forms that I mentioned is the Piqua reactor. And Piqua is a city in Ohio and in the U.S. They had an organic cooled reactor that powered electricity, and that fuel, it's like you have like three annuluses. Each annuluses have like sub-millimeter fins across. You have coolant going through all forms. So there's all these crazy looking geometries. There's a company in the U.S. still looking at kind of flower-shaped fuel rods that the Russians use in their icebreakers. So there are definitely different geometries, and if you want to go a different geometry, the motivation is that you want to increase the surface area you have. So you're basically distributing the heat that fission generates, that tremendous 70,000 times power density. You distribute it around the longer surface area, lower the temperature, and help. But by and large, everything is right now is bare cylinder.
Before we talk about accident-tolerant fuels, let's talk a little bit about accidents. Maybe starting with the very minor sort of fuel failures, and then working our way up in terms of seriousness. What are the current vulnerabilities with our conventional fuels? And then we'll move into, I think, your accident-tolerant fuel area of expertise.
Yeah. So about up to at least 2 years ago, nowadays it's ticked up just a little bit. During normal operation, we're at the 1 ppm level, like meaning that 1 out of 1 million fuel rods experience some kind of a failure, and that failure is really a very like a hairline, like very small pinhole leak. That so you have some gases, some radioactive gases coming out of it. So extremely reliable system for normal operation. And then when you look at anticipated transients, the regulations that we have in place actually tell us that we need to design this fuel such that it will not cause any type of leaks, which is, I think, it's a bit conservative, but
We talked a little bit about transients in our deep dive of the 3 Mile Island accident with James Krellenstein, but just briefly for those of us that are not as educated, what is a transient? It sounds like it's part of normal operations or within
yeah,
definitions of normal.
yeah. So anticipated transients are like the tornado knocks out switchyard, and so now you don't have connection to the grid, so you trip your turbine, and so now you're not generating any power. Then you trip your reactor, you shut it down, and during that, you don't expect any fuel to start leaking. Um, um, so that's kind of, it's kind of robust for that. And then when it comes to accident scenarios, we call them like design basis accident scenarios. So that's like a pipe, starts a main coolant pipe starts leaking out. So there we allow a fraction of this cladding to fail. We don't want significant melting or significant release of fission products and radioactive materials, such that then There's some off-site radioactive, consequence, like we saw in Fukushima. And then there is the last class of accident, which is beyond design-based accidents or severe accidents. And in that case, it's typical that you just assume that this cladding and its uranium oxide has already failed and melted. And you have this, molten cladding with fuel and the surrounding steel structure that we call corium, for a lack of better word.
You have a metallic fuel now, it sounds like.
Pretty much, because the oxygen has gone. And so now you have this, and now you're designing all these other safety systems to make sure that this amount of radioactivity, majority of it, doesn't get out of the containment boundary.
It sounds like it's mainly an issue of containing gases. Is that correct in terms of contamination? I mean, if your reactor kind of catches on fire and explodes as Chernobyl did, that's a bit different. You got solid chunks of fuel and moderator flying all over the place. But with a water-cooled, water-moderated reactor, for instance, is it basically gases that we're worried about?
Yeah, gas and volatiles, right? Some solid material can chemically react, catch on fire, and then disperse. So in an aerosolic manner. So that's what you worry about. So whenever nowadays we have these mobile, we of course have always mobile reacting submarines and everything, but they have also equipped with nuclear weapons to protect themselves. But there are actually people talking about putting reactors on commercial airplanes, like running them. And so that's where the analysis would look at basically like what happens if the airplane crashes and there's an explosion, and can you disperse this fuel material around?
I thought we had thrown that idea in the garbage in the 60s, but who knows? There's lots of startups out there with pretty zany ideas. In terms of our ability to develop new fuels, I think everything in nuclear iterates very slowly because of the kind of reliability standards that are needed and the time it takes to assess those. James has talked before about why SpaceX and rockets are not the best comparison in terms of that impatience that a lot of folks coming from SpaceX or coming from Silicon Valley have for nuclear. It takes, to fail a Merlin engine on a Falcon rocket, it's a 90-second lifespan, and for a reactor coolant pump, we're talking years and years. Similarly with fuel, and nuclear plants need to run ultra reliably. So in terms of developing and testing new fuels, it sounds like that's not easy. And indeed, some reactor designers say, like the folks at GE Hitachi with the BBRX-300, one of their claims is, they're using a pre-existing fuel, and sounds like a big advantage. So just talk a little bit about, in terms of fuel development, whether you're, going to mix up and use something other than uranium dioxide, or even not, if you're just developing a different geometry or whatever else. Tell us a little bit about that process. And I'm kind of seeding the question here, but it doesn't sound like it's easy or cheap or fast.
Yeah. It's fundamentally comes to time. So the regulator wants to know, how does this fuel behave under prototypic normal operation as well as accident conditions. So prototypic normal operation. So our current fuel in the light water reactors, not the heavy water reactors, they're there in the core on average 5 years. So now I want to come up with a new fuel that maybe does a little bit better, 6 years. So I have to put this fuel in a reactor for 6 years. But because it's a new material, I can't put this in the hottest spot of the reactor. I can put this in the non-limiting location, so cooler part of the reactor. But in order for it to get the same amount of exposure as it would get at the hot spot, that means now I have to keep it there, not 6 years, but at least 10 years. So now I've kept it for 10 years. Now I've taken it out, and now I got to do a bunch of tests. In order for me to do tests, I have to wait for that fuel to cool down. I can't just take it out and in these very thick, lead glass hot cells start immediately taking it apart. I have to let it cool down for another 2 years. to design my test, I had to fabricate this thing. It's a fabrication program with quality assurance that requires at least 3 to 5 years. So just by physics, immediately to get one data point, 12 to 14 years away. Now in CANDU reactors, what's interesting is their residence time is actually on the order of like 1 year. So if you want to innovate in the CANDU reactor, you have a much faster cycle. When you look at fast reactors, the situation becomes much worse because the only people who have fast reactors right now is the Russians. The Chinese have just started it one, though it doesn't seem like it's going to be used for research. And India is has more or less started one, but those are the only place. Russia is the only place where you can test it, and we're not friends with Russia right now. So to test it in reactors in the U.S., I need 3 to 5 times the time for this fuel to be there. So I need like 30 years for this fuel to be there. So that's why, when, a lot of people in my community of fuels, like they complain, it's like, why is like a fast reactor company like TerraPower or Oklo, like, why are they coming out, or why are they planning to use this ancient metallic fuel specific, alloys? Well, we don't have a facility to test this in a meaningful time. So they have to build their reactor and then start using their reactor, start testing new things to actually progress. So just fundamentally time kills you. So if you have a reactor that, doesn't, have the fuel qualified, you're looking at a substantial lead time.
Okay, so you're saying that companies like Oklo and TerraPower that are going to operate in the fast spectrum, they either have to qualify fuel for like 10 years in a thermal reactor, a slow neutron reactor, to get the same number, level, or energy of neutron bombardment, or use fuel from the 1960s, essentially, when we used to run some fast reactors. Is that a big problem, or was that fuel pretty good or good enough? Or
so I think this is all I've been discussing then translates to cost, right? I mean, everything, we know the water reactors, we know it works. Heavy water reactors, we know it works. Fast reactors, gas reactors, we built them. We know it can, fission reactions can be sustained and materials don't completely fall apart. It becomes a question of cost. Can the old fuel, and if you don't progress the current fuel technology, can it by itself meet cost targets?
Maybe I wanted to touch bases a little bit and switch into TRISO fuel. It's getting a lot of attention. It's a part of a number of novel reactor designs, the Westinghouse eVinci, for instance, X-Energy and others. Why TRISO? And I want to talk a little bit about it has been used before, I understand, in high temperature gas reactors as early as the 1960s, the Dragon reactor in the UK, Fort St. Vrain, Peach Bottom, a number of high temperature gas reactors. So it's been around for a long time. Let's talk about why, its use case, and I want to talk a bit about what it costs and how we can get those costs down, because it sounds pretty complicated to manufacture.
Yeah. And so why people back then, really old time, they were looking at TRISO fuel. So again, as mechanical engineers, like, what is this nuclear system that you guys are doing? And after a lot of iterations, when the water was, starting to kind of get some steam in parallel, there's all this concept, because, water, more or less, unless you go to supercritical water, which actually the fuel part, the reason why we don't have supercritical nuclear reactors, supercritical water-cooled nuclear reactors today, is that 1960s, 70s fuel solutions, the zircaloy and UO2 or stainless steel, UO2 it's not good enough. You need a new fuel for it.
Because it can't handle the heat?
Yeah, it can't handle the corrosion, the high pressure corrosion environment. That's supercritical water. Now there's more solutions, but so we're limited to the critical temperature of water around 360 Celsius. So we operate our reactors. Of course, we give some margin to that at around outlet temperature of 325 degrees Celsius at the top as the highest, and you run a coal plant or gas plant, you're talking about hundreds of degrees higher than that. And so what does hundreds of degrees higher than that give you? It gives you a higher heat to electricity conversion efficiency. This is how, combined cycle natural gas has been able to reduce its cost over the years. This is how coal plants have gone to ultra supercritical, even water, higher temperatures, again, higher pressures. You're able to reduce your cost, improve your fuel, usage. It's great. So why can't we have that for nuclear? And so that's where this idea came in. If you go to very, very high temperatures, then any metal starts falling apart from a strength point of view. And so ceramics became kind of your friend at these very elevated temperatures. And when you try to do ceramic fuel, what happens with uranium dioxide, if you're operating it at just normal operating conditions, above 800 Celsius on average, those gases, those fission gases that are generated as part of the fission products, most of them are no longer going to get contained in the fuel. At around 1200 to 1300 degrees Celsius, they just come out. And so that becomes a headache to deal with. So what they did was two practical things. One was, hey, this uranium is not great. Why don't we use thorium? So thorium is another element, right, in the periodic table, a little bit below uranium. It happens that when neutron hits thorium, it converts itself to uranium, specifically uranium-233. So it's a fissionable material once it gets converted. But thorium has higher thermal conductivity, better heat transfer, and as well as can actually hold these fission gases much better at these between 800 to 1300 degrees Celsius, much better. So why don't we put that thorium in there? And then why don't we make these things as a little particle, putting a lot of ceramic encapsulation in it, so when these gases gets released, it doesn't really overpressurize the system that much. But now we've reduced the volume. Why don't we just take that weapons grade enrichment, 90% enrichment, married with thorium, voila, I have a system that I can run my reactor at very high temperatures, and I can run, efficiently. So what happened? Because TRISO fuel today, there's no thorium in it, and it's not highly enriched. So two things happen. One is, these reactors ran into a problem on the secondary side. How do you get this hot gas connected to a steam cycle on that side? Steam generator, things leaked, things like that. So those reactors kind of never became really commercialized. And the other thing is that the governments more or less said, no, you can't use highly enrichment for your reactor. You have to use less than 20% enrichment. And so we had to take out thorium from the system and replace it with uranium, because if you put thorium in the system, it just takes all the uranium volume away, and I can't make it work with less than 20% enrichment for these TRISO particle gas reactors. So we
need
had
a very strong neutron source to make thorium work, it sounds like. Is that right?
Yeah,
convert
because
it first. Yeah,
thorium is not fissionable material. You need to first convert it, and because of that, you need more enrichment for it to work at the TRISO level. And so then we have now end up with these TRISO particles that we have today that are roughly 10 to 15% enriched for the larger reactors, and then up to 20% enriched for the micro reactors. And so then the question becomes, they're not going to have as good high temperature capability as the thorium version one. So do you see like the X Energy is one of the high temperature gas reactor vendors that uses this TRISO particle. Their steam temperature is only 40 degrees higher than the UK gas reactors that just use UO2, low enriched UO2 fuel, because you just can't go too high. So that kind of, so now you have the cost that you go in using a TRISO fuel has to justify this additional 50 degrees. And so then becomes, what is this cost? So when you look at the enrichment market right now, the costs have gone up significantly, more than factor 2. What's interesting, though, is that, let's say I have a 15% enriched fuel, and I have a 5% enriched fuel, a factor of 3 times. First thing I got to do, I got to make sure that this 15% enriched fuel gives me 3 times the energy as this 5% enriched fuel. So that's first thing. And thankfully, in the TRISO encapsulation, you can reach that roughly 3 times energy. So that's great. But what happens is that when enrichment prices doubles, this cost, let's say, goes up by 30% for my TRISO fuel. My 5% enriched fuel also goes up by 30%. So they both more or less go up by the same amount. But the problem is we're trying to sell a commodity at the end of this, whether it's heat or electricity. That heat and electricity, you're selling it to someone for a value. So let's say we're selling it for $30 per megawatt hour. If my fuel cost went up by 30% for the TRISO fuel, if it was, let's say, $20 per megawatt hour, it went up by 30%. So now it's around $27 per megawatt hour. My LWR was already at $10 an hour. It went up 30%. Now it's $13 per megawatt hour. So one went up by $7 per megawatt hour. The other went up by $3 or $3.50 per megawatt hour. And that's a problem because you're trying to sell this at a fixed price. So going up by $7.50 per megawatt hour is a huge hit to your overall economics because you had to start with a more expensive fuel because you're enriching more, you need mine more uranium to feed that and everything. Forgetting about all the fabrication costs and everything.
Right. Well, maybe we'll get to that in a second. But on the enrichment side, something that hasn't made a lot of sense to me, and we went through this in our great episode with James, catchy title, check it out in the archives, Enriching Uranium Understanding, was that you need less separative work units to go from low-enriched uranium to HALEU, or high assay low-enriched uranium, than you do from getting natural uranium to low-enriched uranium. And yet, the cost of high assay low-enriched uranium is through the roof. I think it's something like $20,000 a kilogram versus, I think, the enrichment cost for traditional low-enriched uranium fuels around $1,000 or a little more than that. First, correct me if I'm wrong on those numbers, and why? Why is that we need maybe, tell us how many SWU we need for, to get to each, but, why is it that there's such an extraordinarily higher cost on high assay low-enriched uranium?
Yeah. Fundamentally, when you go above 10% enrichment, you're looking at a different category of operation classification. And so what that means is that you have to have different form of quality assurance. You have to have different forms of, and the quality assurance is very much related to safeguard of this material. And that's one of the, cost drivers that, something that's greater than 10% enriched will never be, unless we, dismantle the regulatory body and streamline everything, in today's environment, that's always going to be very hard to compete with something lower.
So increased safeguarding costs is to avoid someone, nefarious turning it into weapons.
Yeah.
Does that just mean hiring more SWAT teams?
More security guards,
fences?
more cameras,
Okay.
more. And then the other part is just the inertia. Right now, everything is licensed for less than 5%. There's a lot of activities to get it to 8% right now in the U.S. Some activities, lower kind in Europe. But then you have to build up all these new centrifuges to that enrich. So, it's just like building a new capital investment. Somebody has to pay that capital investment off. And then once that's paid off, then you're just paying off the operation. So it's just amateurizing this massive investment that you need to do, all these filings you have to do with the regulator and putting up the factory and everything in. That's the other part of it. Why that doesn't, why the enriched, 15% enriched ends up being more expensive per kilogram than
The other thing I heard, and I think this was from someone in the Canadian fuel industry, I mean, we're working with natural uranium. I'm not sure if it's impossible, but I think it is to sort of have an accidental criticality. But when you get up to 20%, tell us a little bit about that. It sounds like that's another cost driver, is you just have to be a lot more careful with handling.
Yeah, and that's kind of an unfortunate thing, in the United States, we deal our criticality safety based on enrichment. In reality, it should be, affinity of that, fuel to reach fission reaction. So like if I go from like UO2 to something like more dense that I can pack more uranium into it at the same enrichment, well, that, I should be more worried about that. Enrichment shouldn't be the target. But overall, all things, minor things aside, if you increase your enrichment, you have a higher potential to reach a fission reaction by, getting the truck that's covering it, let's say, it dumps into the ocean or something, and you lose all the, the absorbers around. So you have to have, there's much more focus to make sure that you're not concentrating a lot of these materials in a single batch and distributing it. In the natural uranium world, yeah, you don't worry about it at all. That's why you're, in the CANDU reactors, the prices are more sensitive to uranium price, versus, enrichment, you're kind of immune to it. Another actually interesting thing about CANDU fuel, because I've been doing a lot of work on CANDU type fuel as a part of supporting a company looking to increase the burn up of CANDU fuels, is that most of its cost, again, sensitive to uranium prices, is low enriched, but you're only getting a fifth of the energy out of it as opposed to a water-cooled reactor. And because of that, where you actually pay for it more is on a disposal side. So you end up with much larger disposal cask, that's okay, but that's not sensitive to uranium prices or fluctuations. That's just the cost of that is tied to inflation. So back in 5-6 years ago, where uranium prices were, 3 times less, when you account for the, spot prices of uranium enrichment and disposal, the CANDU fuel and the U.S., higher burn-up light water reactor fuel, they were kind of similar in cost. CANDU fuel were actually a little bit less because you get a long-term price for Ontario Power Generation to dispose these in dry cask. It's actually the government kind of, subsidizes a little bit. And so you get actually a little bit less, but overall, everything's, let's say, even, it'll be similar. But now uranium market has exploded and enrichment has exploded. So now the fuel side of things have gone up for the water reactor side as well as the CANDU side, but the disposal side hasn't changed much, just based on inflation. So now you have the CANDU fuel substantially cheaper than light water reactor fuel per energy generated, which is, we haven't seen that for a long time.
In terms of the actual fabrication of the fuel, again, leaving aside the enrichment, how much of that is a cost driver for, say, CANDU versus light water reactors versus TRISO? Because, again, just looking at the fuel costs as they currently stand, I'm very interested in what they can get down to. Let's maybe focus on TRISO for a second. So a TRISO-fueled reactor like the Westinghouse eVinci, the initial fuel load, it's not publicly available, but 1, 2, 3 tons maybe of high-assay low-enriched uranium that's required. And it's in a TRISO form, I believe. So the current cost is high 20,000s per kilogram. And if you run some calcs on that, the numbers I got was the initial fuel load is like $30-40 million for a 5-megawatt reactor. Now, you can maybe justify that as, okay, but across 10 years, maybe, that cost is what the diesel would cost you to run, a 5-megawatt diesel reactor. However, the upfront cost of a 5-megawatt diesel reactor is like $1 to $2 million. So massive addition to the CapEx, essentially. Fuel's usually an OpEx on those reactors, which I think makes them economically very tricky. if we scale up, and it's a chicken and egg problem because you need a big reactor fleet to justify the investments to make lots of HALEU and TRISO, what do you think, based on your knowledge and understanding, is sort of like the basement price we could get HALEU and TRISO down to, given some of the complexities we've discussed?
Yeah, no, that's a great question. So again, it's important, just like that disposal cost that I just mentioned, fabrication cost. Again, not really, hasn't been doubling or tripling. It's, goes up by, some different indexes of inflation. And so when the uranium side goes way up, the percentage of the fabrication cost of the overall becomes very little. Now, what is that? So for CANDU technology, for natural uranium, that fabrication cost tends to be 30% or so cheaper per kilogram than the fabrication cost for a light water reactor. When you look
Is
at,
that because the fuel is like these little bitty kind of log shape? They're not crazy long.
it's simple. Yeah, it's a lot simpler to deal with. First, it's not enriched, so again, less quality assurance. Doesn't have burnable poisons. It doesn't have fancy what people call like Swiss watch type of looking mixing vanes, and you just have a kind of a crude spacers that holds them together, sitting in the horizontal. It's a little mini thing, so it's just not as complex. And then when you look at a TRISO fuel, the volume is smaller, and so per kilogram, suddenly you're talking about, more than 20 times more expensive than a conventional light water reactor. But then you have to account for the better thermal to electricity efficiency, the more energy that it gets extracted. And so when you put it all even out, depending on, if you're the eternal optimist, you can get it arguably to 1.5 times a light water reactor. If you use like, new prices, you got somebody's got to pay for these capital investments and things like that. You're looking at 2 to 3 times that for a commercial gas reactor. But then if you're talking about, your example is kind of a very niche example, like Vinci. It's targeting a very long cycle. It's using a technology called, it's a heat pipe cooled reactor. So the heat pipe itself sucks a lot of the neutrons, so you need additional enrichment. So there, in that case, you could be looking at 8 times the overall dollars per megawatt hour. But to put these things into context, I always use the example of natural gas. So we started this podcast by saying it was 70,000 times more energy per kilogram. If you look at the price of natural gas, $3 per million BTU. Conversion to gigajoules, I think you guys use maybe gigajoules, is similar. If you look at that $3 number, with the current uranium contracts that some utilities are able to score, which comes out around roughly $15 per megawatt hour for the light water reactors, $3 is less than 2 times that. So 70,000 times, we had a 70,000 times advantage. That's all got washed out because uranium, much more expensive to dig. It's not like natural gas. You go Texas, look at the site really hard, and suddenly gas comes up. You got to dig it out. You got to purify. You got to convert it. You got to enrich it. You got to go through all this quality assurance. So that completely washed out. Now we're talking about a factor 2. When you look at TRISO fuel for a commercial reactor, natural gas has to be $5 for it to be competitive. And this is very, very important because if uranium prices keep going up and nuclear fuel, as we know it, cannot compete with the price of fuel for natural gas, then a lot of the market, which is both the grid and industrial application, completely goes away, because even if we get our reactor, for very, very minimal cost, the operation and maintenance cost, just the whole operation of things, we're already, puts us in a uncompetitive way. So we have to do whatever we can for the nuclear fuel price to be competitive with natural gas using that 70,000 times more energy. And once you put in TRISO fuel or HALEU type of product, or the microreactor way of just one fuel for the rest of it, it's just not even going to be competitive with the price of natural gas.
You said you put on your optimist hat to say sort of 1.5 to 2 times the cost, TRISO versus LEU. In terms of your realist hat and this chicken and egg problem of needing a sufficiently large reactor fleet of reactors using HALEU and TRISO to generate the capital investments in the fabrication facilities to make it. A, I mean, what do you think the realist case is? And B, how long do you think that would take? Everything seems to take a long time in nuclear.
Yeah. No, I mean, everything, on the fuel side, I was at, 10 to 15 years. But as I mentioned right now, for the current, TRISO fuels cost, I wouldn't be surprised if we see something on the order of $40 per megawatt hour, given the current market trajectory. Again, just, even a couple of years ago, talking to some utilities, they were, excited. They were like, oh, we're glad we saved our company millions of dollars by extending our previous fuel contract, for another like 5 years. And it's like, well, it doesn't seem like the market's going to cool off anytime soon. We were talking about, we had $5 per megawatt hour dollar in light water reactor work, which was similar to the, can do side. And when you account for the disposal, and now the new contract, we're talking about $15 per megawatt hour for our fuel. And so, even the light water reactor one, it's no longer negligible. Natural gas, right now it's, I think, more than $4 because it's wintertime, but overall, seeing around $3 on average.
So just to make sure that I'm getting this correct in terms of these various ratios, because we've used some different comparators, the cost per kilogram. Let's stick with the cost per megawatt hour of fuel. I don't know if you can rattle it off by memory, but CANDU versus low enriched uranium, light water reactors versus TRISO versus natural gas. In terms of cost per megawatt hour, the fuel cost. I don't know if you can, if you have a good trivial pursuit of nuclear fuel costs.
Yeah. No. I kind of live for all this. This stuff.
All right, cool.
Yeah. So for CANDU fuel, again, you have a very long-term contract for disposal that is very, very nice. So let's talk about maybe cost, that what it would be for, let's say, new contract. Let's say for CANDU fuel, you're looking at between, depending on your regional, $6 to $8 per megawatt hour electric. For water-cooled reactor, whether it's a large water-cooled reactor or a small water-cooled reactor like the BWX300, you're looking at $13 to $16 per megawatt hour electric. And then TRISO fuel, depending on commercial all the way to microreactors, you're looking at $30 to $85 per megawatt hour electric. And then commercial natural gas, highly depends on regionally, but you're looking at $25 to around $40 per megawatt hour electric.
All right. You had one thing you mentioned to me prior to recording, that the cost of the BWX300 fuel at OPG might be expensive. Can you explain that?
The current fuel, with the current contracts, they're likely paying well under $7 per megawatt hour electric. If you account also disposal, the fuel itself is very, very cheap, and much cheaper than $7 per hour. And I just told you that if you're talking about a new LWR, it's $13 to $16 per megawatt hour, more than factor 2. And then we'll see what happens. And I don't want to, I still, on the economic side, I don't account any tariffs yet in the equation.
Oh,
things change rapidly as we've seen. But if you add, additional tariff for this fuel, because, Canada, A, doesn't have enrichment. BWX300 is a light water reactor, it needs enrichment. And B, Canada does not have boiling water manufacturing, fuel manufacturing. And so it has to come from, somewhere outside the fuel itself. So if you add those tariffs, and then because the fuel is coming from long life, Canada to U.S. is not too bad, right? The poor folks at UAE, they signed up for a light water reactor, which comes with it. Where are you going to get the enriched fuel from, which U.S. doesn't like countries to enrich. Koreans, they have a healthy program. They don't they don't have enrichment. So you have to ship things all over the world, and that transportation costs, which is tied to fuel costs overall, which has gone up quite a bit substantially since the COVID period. So that has escalated. So unless Canada has its own, factories, that additional transportation cost adds another few dollars per megawatt hour to the fuel. And now you're suddenly looking at, 3 times per energy production.
Koroush, there's so much more I had down here to ask you about, but we're up over an hour now. Always a pleasure. Love the encyclopedic mind there, and then I can ask you random esoterra and you can rattle it off. Thank you for making the time. Looking forward to our next show together.
Yeah, thanks for having me, Chris.